Hello, all my beautiful math people out there. Today we are going to take a look at the Pythagorean Theorem, which states that in a right triangle, the sum of the squares of the legs equals the square of the hypotenuse. So we have to tend to a couple of vocabulary words here for a minute. What are the legs and what is the hypotenuse of a right triangle? Let's take a peek here. I'm looking here, and I see that the legs represent the two sides of the triangle that form the right angle. So if I'm over here on this triangle, you can see that in blue I have one leg over here. I'm going to just make sure I got a small thing to write with, right? Okay, so this is a leg, and down over here this is another leg. And it's really kind of neat to think about too, because when I say the two legs make the right angle, not only do they make a right angle, but they also make the letter L. So you can kind of remember that. The two legs make the L, and your 90-degree symbol, your right angle symbol, is smack in the center. Okay, so that's something to recall. The hypotenuse is the longest side of the right triangle, and it's always opposite from the right angle. So if you were standing right here at the right angle, and you were saying, hey, here I am, then the side that's opposite from you definitely would not be one of the sides that touch you or that help create you. You'd not end up being opposite by using one of the legs. Opposite would be way over here, and this is called the hypotenuse. So let me go ahead and write hypotenuse up here. And I think of a hypotenuse as being a great big long word, and it corresponds to the great big long side of your right triangle, regardless of how the right triangle is drawn. If the right triangle is drawn this direction, you see these two pieces right here that make my legs? They make my right angle, so they are my legs. And then this last piece up here is your hypotenuse. Okay? Hopefully that makes pretty good sense to you. All right, now let's see what this really means as far as algebraically. If I take the sum, the word sum here, I have to take the word sum, and I have to obviously do a plus sign here, right? The sum of something. The sum of what? The sum of the squares of the legs. The squares of the legs. So the sum of squares. So something is being squared and something is being squared. This means the sum of the squares. The sum of the squares of what? Of the legs. So this is leg 1 and this is leg 2. And since the legs are interchangeable, it doesn't matter which order you write them in. So this gives me the sum of the squares of the legs equals, big fat equal sign right here. Boop, boop. Oh, we knew this was going to happen eventually. This is equal to, and let's make that nice, the square of the hypotenuse. So squaring something again. And what am I squaring? I'm squaring the hypotenuse. So hypotenuse, and I'm going to leave myself a little bit more room here to finish writing hypotenuse squared. So this is your Pythagorean theorem. Leg squared plus leg squared equals hypotenuse squared. You will see me writing this like leg squared plus leg squared equals hypotenuse squared. And of course, I know that you've seen this before, and when you have seen it, you have been given a picture of a right triangle, just like this. The legs have said A and B, and the hypotenuse has said C. And then you have learned the Pythagorean theorem as A squared plus B squared equals C squared. But you got to make sure that the C is definitely the hypotenuse. Okay? So the two little ones, you square them and add them up, and you get the big one squared. All right? Let's go a little bit further geometrically here. Okay? So I have this picture. And as a matter of fact, I think I'm going to move this picture just a little bit over here. We're going to move this. Very good. And I'm going to talk about what this means as far as geometrically. Okay. So I'm going to slide myself up here a little bit. Get back to here. I think I'm going to pick a different color here. It says if I take one of the legs and I square them. So I'm literally going to build a square on the leg, if you don't mind. So I'm going to, this leg right here looks like it's 1, 2, 3 units high. So I'm going to go 3 units over, 3 units down, and 3 units back. I have now created a square that's 3 by 3 by 3 by 3 on the side of this triangle. So I have squared the legs, so to speak. And if I look at that area that's inside this square, 3 times 3 is 9, so this area is a 9. Now I'm going to use the other side, the other leg, and I'm going to square it. And this is going to be a length of 4, and a length of 4, a length of 4, and there is a length of 4 already over here, if you will, along that side. So this is a 4 by 4 by 4. I don't like that 4, so I'm going to get rid of it and do it again. And this is a 4 right here as well. So 4 times 4 gives you the area of this square right here. That gives you 16 little squares inside of that square. Alrighty. Now if I add these up, if I add the 9 and the 16, I add them up, and that gives me 25, which guarantees me that it would take 25 little squares to build on my hypotenuse. So if this is a length here, whatever length that is, you just try and eyeball it, follow it out, and build a square. So you are guaranteed that there will be 25 little squares inside this big square. The area of this square built off your hypotenuse is 25. And that works. Now, what would the sides of this square have to equal in order for the area to be a 25? And I'm hoping you know that 5 times 5 is 25, so therefore this little question mark here becomes, yikes, becomes a 5. This is a 5. I could probably turn that into a 5, couldn't I? Just by doing that. This up here gives me a 5, and this over here gives me a 5. So geometrically, if I were to take one leg and square it, I end up with a 9. I take the other leg and square it, and I end up with 16. You can see this geometric representation right over here on the left-hand side. And then my last hypotenuse would be a 5, and I square the hypotenuse, and this gives me 25. It is true that 25 is equal to 25, and we have just verified the Pythagorean theorem for this 3, 4, 5 triangle. Alrighty? Well, that being said, if you can find 3 integers that verify the Pythagorean theorem, then you have what's called a Pythagorean triplet. So we have just learned about our first Pythagorean triplet. So I'm going to come back up here. I'm going to get down. I'm going to write Pythagorean triplets. When we give the Pythagorean triplets, we usually give them in a set of parentheses, brackets, I'm sorry, not parentheses, and from small to big, so 3, 4, 5. So 3, 4, 5 represents the sides of a right triangle, and if you definitely have a right triangle, well then 3, 4, and 5 are going to verify the Pythagorean theorem. Now I could take a 3, 4, 5 triangle and I could double it in size. Let's see if I did that. If I took a 3, 4, 5 triangle, this is roughly 3, 4, 5, and I doubled it, that would make the 3 become a 6. Let me see, 1, 2, 3, 4, 5, 6. I went just a hair too far here. It's going to erase the whole thing. I knew it. 1, 2, 3, 4, 5, 6. And then I come over here. 4 times 2 is 8. So I make that an 8. This is a 6. Then guess what happens with this hypotenuse? This is going to automatically become a 10. So if a 3, 4, 5 represents the sides of a right triangle, and you can blow that up, then 6, 8, 10 is going to also represent the sides of a right triangle. As a matter of fact, these two triangles are similar with each other. You've learned that in your geometry class, I hope. And similar shapes have the same basic shape, but their units of measurement are proportional. Okay, so like their sides, their linear values are proportional. So 3 compared to 6 is going to be the same thing as 4 compared to 8, and 4 compared to 8 is going to be the same thing as 5 compared to 10. So this means that the sides are proportional. Sides are proportional. Alrighty. And I can't help myself here, but when I say the word proportional, that means I can build proportions, which means like 3 over 6 equals 4 over 8. And a proportion is when a fraction is set equal to a fraction. Or I could say 4 over 8 is the same thing as 5 over 10. Or I could just use the first one and say 3 over 6 is the same thing as 5 over 10. But instead of writing these out 1, 2, 3 times, we just write them out like this. It means the same thing. Okay, I get 3 proportions out of this equation up on here. Alrighty, so 3, 4, 5 is a Pythagorean triplet. That also means that 6, 8, 10 is a Pythagorean triplet. And instead of doubling my sides, so instead of just taking this triangle and timesing it by 2, I could have times by 3, and I'd be talking about the same relationships. So if I times by 3, I'd be looking at a 9, 12, 15 triangle. It's just 3 times as big, but it's still going to be a right triangle. And maybe I didn't multiply by 3. Maybe I'm multiplying by 4. This will give me a 12, 16, 20. And I can keep doing this, okay, to get more and more triangles that are the same basic shape as your 3, 4, 5. So 3, 4, 5 is a Pythagorean triplet. I'm going to give you a few more Pythagorean triplets. Let's see here. Let's go with a 5, 12, 5, 12, 13. And let's prove that this is a Pythagorean triplet and verify it by doing leg squared plus leg squared equals hypotenuse squared. So if this is a right triangle, then the hypotenuse would have to be that 13 because we are talking about the longest side being the hypotenuse. So I put a 13 in for the hypotenuse. And the legs, remember, the legs are interchangeable, so it doesn't matter which one goes where. We're going to do the same thing to them and add them up anyway. So I'm going to put the 5 and the 12. 5 squared is 25. 12 squared is 144. 13 squared is 169. When you add 25 and 144, you get 169. So 169 equals 169. That works. So that means that a triangle with sides 5, 12, and 13 has to be a right triangle. Now I can double that 5, 12, 13, and I can call it a 10, 24, 26. So a 10, 24, 26 triangle is nothing more than a 5, 12, 13 blown up to be twice as big. Therefore, the shape is going to basically remain the same. It's just going to be a different size. Instead of multiplying by 2, I could multiply by 3. This would give me 15, 36, and 39. And I'm taking these numbers down here, this 5, this 12, and this 13, multiplying each of them by 3. I could multiply them each by 4, and so on. There's no end to the number of Pythagorean triplets that I can make from a 5, 12, 13. Just like there's no end of the Pythagorean triplets I can make from the previous 3, 4, 5 triplet. Okay? Now here's another triplet for you. Just because, you know, you're taking your ACT, your SAT, whatever you're doing, the more triplets you know off the top of your head, the easier your life is going to be sometimes. 8, 15, 17 is indeed a Pythagorean triplet. Whoops. Remember? Brackets, not parentheses. And that's because if you square 8 and you square 15 and you add them up, you get the square of 17. And that works every single time. You can verify that yourself if you'd like to pause the video and do that. However, if I can double my 8, 15, 17, that would give me 16, 30, 34. That is another Pythagorean triplet. Or instead of doubling my 8, 15, 17, I could triple it. So I multiply the 8, the 15, and the 17 by 3. That would yield 24, 45, and 51. Or if I, instead of by 3, if I wanted to multiply by 4, or by 5, or by 6, there are an infinite number of Pythagorean triplets that are similar to the 8, 15, 17 triangle. Alrighty, I'm just going to throw another one out here. 7, 24, 25. Whoops. 7, 24, 25 is also a Pythagorean triplet. And yes, you can double it, you can triple it, whatever you'd like. This would give me, what would this, 14, 48, 50, if I just doubled. And of course, you can keep right on going. There are more Pythagorean triplets, many, many more. There's an infinite number of Pythagorean triplets. However, they are very, very special because of all this squaring that goes on with the legs and the hypotenuse. when you know some legs and when you know two pieces of a right triangle and you're trying to find the third, then you're going to have to undo a square, which means you're going to square root. And only so many numbers have perfect square roots. So our triplets are really important. Okay, let's see how many triplets I gave you here. I gave you this 3, 4, 5. I gave you the 5, 12, 13. I gave you the 8, 15, 17, and the 7, 24, 25. I think I'll just give you one more that comes off in my mind here, which would be 11, 60, 61. But I'm pretty sure I've given them to you in the importance of where you'll see them. The 3, 4, 5 is very, very common. It's actually the only Pythagorean triplet that has three sides whose measurements are consecutive integers. So 3, 4, 5 is the only Pythagorean triplet where you'll see the numbers going up by 1 in each case. So for example, 4, 5, 6 is not a Pythagorean triplet. 11, 12, 13 is not a Pythagorean triplet. 1, 2, 3 is not a Pythagorean triplet. 2, 3, 4 is not a Pythagorean triplet. Only 3, 4, 5 has consecutive integers for measurements and fits the Pythagorean theorem. All right, so now we have the Pythagorean theorem down. Let's see how we will use it to solve some of our questions, okay? I'm going to switch colors just because I can. Very good. Alrighty, I am going to start with, let's say I give you a picture, and I don't want to be playing around with drawing things to scale, so you guys are going to have to forgive me. None of my pictures are really going to be drawn to scale. Okay, so here's an example for you. Let's say I have a right triangle like this. My right angle's up in the middle. I have a 3 here. If I draw this down here, this becomes a 5, and I want to know what this leg is. So I have a 3 on a little leg, I have a 5 on the hypotenuse, and I have an x on a longer leg. I would do my Pythagorean theorem, which tells me that leg squared plus leg squared equals hypotenuse squared. My hypotenuse, I think, clearly is a 5, right? And the legs are 3 and x. So 3 squared is 9, x squared is just x squared, and 5 squared is 25. So if I want to solve for my x, I'm going to have to subtract 9 from both sides of the equation. I end up with x squared is equal to 16. That gives me x is the square root of 16, or x is 4. Now I know when you introduce a plus sign, when you introduce a square root sign, you're supposed to introduce a plus or minus sign. However, I know that x represents a positive length of the side of this triangle. So I'm going to just not write the plus and minus every time, because I'm just going to eliminate the negative sign anyway. So x is 4. Hey, look at that. If x is 4, shouldn't I have known that off the top of my head? I should have known that x is 4, simply from the Pythagorean triplet that we just did. So if you see a 5 on the hypotenuse and a 3 on one of the legs, the other leg has to be a 4, and there's really no need to do any of this work because you have that knowledge off the top of your head. Alrighty, now if you don't want to memorize any triplets, then go ahead. Feel free to do all this work anytime you want. But the more little things you can learn off the top of your head, the better. It's kind of like your times tables, right? If you don't know that 7 times 8 is 56, you're going to have a fun time figuring it out every time it's asked of you. Okay, here's another question for you. Let's see. I'm going to draw this triangle like this time. And I am going to put a 24 here. I'm going to put a 32 here. And I'm going to put an x here. And I want you to find x. Pythagorean theorem. You definitely have a right triangle, and therefore it is true that leg squared plus leg squared equals hypotenuse squared. The hypotenuse is the thing I'm looking for. That's my unknown, x. And the two legs are 24 and 32, right? They are the ones that make your right angle. So if I take 24 and I square it, I get 576. If I take 32 and I square it, I get 1024. This is equal to x squared. I add those up, and that gives me 1600. So I'm going to write x squared equals 1600. And then x would be the square root of 1600, which means x is 40. And for me, I think, wow, that's kind of neat that I got a whole number answer there. I wonder if maybe I could have done this a little bit differently. I'm going to go ahead and write my 40 up here. So I'm going to show you a little trick, maybe. Call it a strategy. If I say trick, people listen more than I say strategy. Let's see this original question again. You see the 24 and you see the 32. Do you recognize that 24 and 32 are both multiples of some number? And what number would that be? I'm hoping you're saying 8, and I think that's a good thing. So what I'm going to do is I'm going to divide these sides by 8. And when I divide by 8, I shrink this triangle. I shrink it a lot more than I just shrunk it, but the idea is it gets smaller. 32 divided by 8 is going to give me a 4 here. 24 divided by 8 is going to give me a 3 here. And I know my Pythagorean triplet is a 3, 4, 5 with the 5 on the hypotenuse. So this has to be a 5. And if this has to be a 5, I can now multiply by that 8 to bring 5 times 8 back up and just get 40. And again, all of this work, didn't need to do it. If I recognize that 24 and 32 had a common factor, the biggest common factor possible, please, okay? Break the triangle down, shrink it, because now these two triangles are similar to each other. They have the same basic shape, but different sizes. As a matter of fact, I don't think, there's no way that I listed under my 3, 4, 5 Pythagorean triplets above the 24, 32, 40. But it certainly would have been in that list after the ... part. Okay, this is the symbol for similar. These triangles are similar, and therefore their sides are proportional. Alrighty, let's go ahead to example 3 and see what we have here. I have a picture like this, and like this, and like this. I have a right angle right here. That doesn't surprise you. I'm going to put a 30 here. I'm going to put a 34 on the hypotenuse, and I'm going to say find the other leg. So let's see what we can do with this. You want to do a shortcut? You want to do Pythagorean Theorem? What would you like? Let's do both. Let's do the Pythagorean Theorem first. So let's go ahead and say something squared, leg squared, plus leg squared has to equal hypotenuse squared. That's my Pythagorean Theorem, and I'm waiting for my legs and my hypotenuse input. The hypotenuse is the 34. I can see it's across from my 90. See this? Opposite from my 90. And the two legs, of course, make up the right angle, so I'm looking at x squared and 30 squared. This gives me x squared plus 900 is equal to, now 34 squared is 1,156. I subtract 900 from both sides of the equation. That gives me x squared is equal to 256, which means x is the square root of 256. And I don't know if you know it or not, but I know that that's 16 for my x. So this is definitely going to be a 16 up here. Let's see if we can find a little shortcut. Okay, let's do this. What do 30 and 34 both have in common as a factor? Not much, but just a 2. So we're going to divide everything by 2, and we're basically going to shrink our picture. 30 divided by 2 is 15. 34 divided by 2 is 17. So do you recognize a triplet that has a 17 on the hypotenuse and a 15 on one of the legs? I'm sure if you look back, you'll see it definitely is. That means that this has got to be an 8 right here for your 8, 15, 17 triangle. And then I simply multiply back by 2, and 8 times 2 will result in that 16. And then all of this wasn't necessary. So we got to try to think smarter, not harder. Not every time, though, are you allowed to think smarter, not harder. Sometimes things just get tougher, I guess. Okay. So, let's go ahead and think about something that's not a triplet. So we're not going to have a little shortcut on this. Let's go for example 4 here. Let's see what happens if I give you something that's, instead of a 3, 4, 5, how about a 5, 6, and an x here? And I don't like that right there. That's much better, even though it didn't meet, but there you go. So I'm looking at something squared plus something squared is equal to something squared. Leg squared plus leg squared equals hypotenuse squared. The two legs are 5 and 6, and the hypotenuse is my x. 5 squared gives me 25, 6 squared gives me 36, and that is equal to x squared. 25 plus 36 is 61 equals x squared. which means that x will be the square root of 61. And for your purpose, you can probably throw that right into a calculator and get a decimal approximation for that. This is approximately, with my calculator, 7.810249676. Okay, and notice that 7.81 would definitely be the longest side of that triangle right there. Okay, so we would be done with either of these two answers right here, depending upon how your teacher asked you to leave the answer. All right, let's move along to example 5. And let's see, I have another triangle for you. Let's do something like this. Right triangle right here, right angle right here. Here's a 7, an x, and a 20. I want you to find x. So leg squared plus leg squared equals hypotenuse squared. The legs are x and 7. Yes, those are my legs making up my right angle. And the 20 is the hypotenuse, which is the longest side of the triangle across from the right angle. This gives me x squared plus 49 is equal to 400. Subtract your 49 from both sides of the equation. Where's my little... And I end up with x squared is equal to 351, which means x will be the square root of 351. I don't know what I could possibly do with that. I don't know. I suppose I could break it down by 3, could do something else with it. Let's just throw that into a calculator, and that is going to give me 18.734994. So there you go. Those are my two answers, and it's about 18.73. So it makes sense because each leg has to individually be shorter than the hypotenuse. So that works. Alrighty, let's move on to example 6 here. And I will give you a triangle that looks something like this. You're going to find x right there. If I give you a 5 root 3 on this leg and a 10 right here. All right, so we're looking at leg squared plus leg squared equals hypotenuse squared. And you know, this whole thing that I'm doing is all about Pythagorean theorem. But you know, in a problem, when they tell you to solve for x, they're not going to say use the Pythagorean theorem to solve for x. You need to look at a right triangle and you go, oh, I know that the Pythagorean theorem is used for a right triangle when you know 2 of the sides and you want to find the third. So you have to come up with the idea to use leg squared plus leg squared equals hypotenuse squared. All right, well, one of my legs is x, the other one is 5 root 3. Hypotenuse is a 10. So this gives me x squared plus, now I need to do 5 root 3 squared. That gives me 5 root 3 multiplied again by 5 root 3. 5 times 5 gives me 25. Root 3 times root 3 gives me 3. And 25 times 3 is 75. Equals 100. Subtract the 75 from both sides of the equation to solve for x. I get x squared equals 25, which means x is 5. Interesting. I got a really nice whole number here for an answer, even though I started with a 5 root 3 someplace in there. That won't be such a surprise to you as we move on. But for right now, we'll leave that. X equals 5. And does it make sense that you can have a 5 here? I hope it does, because 5 is less than 10, and each of the legs has to be less than the hypotenuse individually. Okay, so example 7, we'll wrap it up for us. Let's say, for instance, don't like that picture. Let's say, for instance, I have a triangle where both of the legs are equal to each other. I'm going to give you the hypotenuse as 6 root 2. And, you know, I just don't quite like it. There we go. So I'm going to, yeah, I don't like that either. Let's change this just slightly for me. That's close enough. Okay, hypotenuse is 6 root 2, and your job is to find x. Well, if I told you that this is an isosceles triangle, then you should know enough to put another x down here. And now we're working at leg squared plus leg squared equals hypotenuse squared. Both of the legs are x's, and the hypotenuse is a 6 root 2. This gives me x squared plus x squared equals, let me see, 6 root 2 and another 6 root 2. When in doubt, write it out. This is 2x squared equals 6 times 6 is 36, and then square root of 2 times the square root of 2 is just 2. So that gives me what? 72 over here, and this is 2x squared. Divide both sides by 2, and x squared equals 36. Square root both sides, x will have to equal the square root of 36, and positive at that because I know it represents the side of a triangle. So x is 6. That's pretty nice. And if you continue to watch one of my next videos, you will have been able to have done that right in your head, and all of that would have been for nothing, because I'm going to teach you something special in the next video. Okay, so stay tuned for my 2 special right triangles, which will allow you to do this in your head and that in your head. So 6 and 7 are going to be on the next video as well someplace. Okay? All right, you guys. Lastly, I would be amiss if I didn't say it. Come on, move up. It won't move up. Okay, so I'm going to pick a really bright color here, and I'm going to get really big on it, and I'm going to say, Talon out. Whoop, whoop.